today we're going to be talking about basic binomial probability for genetics. Now, oftentimes you'll have events that can be one way or another. So in genetics, we can talk about boy or girl, we can talk about wrinkled or smooth, and these are what are called the outcomes of something called a Bernoulli trial. The Bernoulli trial is basically an event in which there's two outcomes, this or that, yes or no, oftentimes determined as or defined as success or failure. And these can be given, in the case of boys or girls, probability 50-50, heads or tails 50-50, but sometimes it's not 50-50, and you can give a variable, p, which defines a probability of a success or some event. Now, of course, if this were the case, then the other option, instead of this is for heads, then q would be tails, and of course the probability of p, okay, is equal to 1 minus q. Okay, and the probability of q, of course, is equal to 1 minus p, because the two of those are the only options, they add up to 1. Now in the case of, let's for example, think of boys and girls. Okay, now there's two important things to understand when trying to understand binomial probabilities. These types of Bernoulli trials are considered independent, so the chance of one event happening doesn't affect the chance of another event of happening. So as we all know, the chance of a single boy in one family of one child is equal to a half. The chance of two boys in a family of two siblings is 1/2, right, times 1/2. And that's because these are independent events. Okay, so in the case of independent events, you can multiply it to get the full probability. So of course the probability of 3 girls in a family of 3 children would be equal to 1/2 times 1/2 times 1/2. Or to simplify things, you could say 1/2 to the 3rd. Okay. Now, things get a little bit more complicated when we're talking about more complex things. So you can easily calculate, given this, the probability is, for example, there's 5 children, that all of them are girls. Probability that there's 27 children, all of them are boys. It gets a little bit more tricky when you're talking about, say, for example, well, in a family of, say, 7 children, there are 3 boys. How do you do that? Well, let's just think of the simple case, okay? Let's just, in fact, think of a case in which there are, say, 7 children and one of them is a boy. Okay. Well, what are the ways in which you can have one of them be a boy? Well, you imagine that there are 7 children, 1, 2, 3, 4, 5, 6, 7, okay? Well, one way in which there can be one boy in a family of 7 is if the first one is a boy, okay, and this one is a girl, 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 right? And what's the probability of this exact event, specifically the first one being a boy? Well, it's kind of similar to what we had before. It's a half times a half times a half. In this case, the chance of a boy being here, and then a girl, then a girl, then a girl. So in this particular scenario, we'd say that the probability of this scenario, i.e. the first is a boy, probability first is a boy, followed by all girls, okay, is equal to, again, 1/2 to the 7th, okay? But we're not actually interested in this. We're not just saying what's the probability that the first is a boy. We want to know what the probability that there is one boy, okay? Well, in order to do that, you have to think of all the different ways in which there can be one boy. And in fact, there are many different ways. Well, actually, there are 7. This is one way. Another way is if the first one was a girl, okay, and the second one is a boy, okay? So you can quickly see that there are 7 ways for one boy, okay? And in fact, what you can consider is another class of events which are sort of sums of more complicated events which are mutually exclusive, okay? These different ways for there to be one boy in a family are mutually exclusive, because if there's one boy in the family and the first is a boy, then the family cannot also have the second one be a boy. When these complex events are mutually exclusive, to get the actual sort of total probability of that complicated event, you just simply have to add up these mutually exclusive probabilities, which you have already determined, because the single types of ways in which you can get one of these mutually exclusive probabilities is because these things are independent. So in this particular case, for 7 children, the probability that there's one boy in the family is equal to 1/2 to the 7th. Okay, this is the case in which the first is a boy. Okay, plus, because it's mutually exclusive, the second one being a boy. Second is a boy. Plus 1/2 to the 7th for the third being a boy. So on and so forth, okay? Plus 1/2 to the 7th, plus 1/2 to the 7th, and all the way until the last one is a boy. 1, 2, 3, 4, 5, 6, plus 1/2 to the 7th. And a simpler way, of course, writing this is 7 times 1/2 to the 7th power. Okay, well this is easy to do because we know how to sort of quickly count all the ways in which there can be one boy in a family of 7. Well, let's think of something a little more complicated than that. Let's think of a family of 7, and we want to know what's the probability that there are 3 girls in the family. Well, we imagine our slots: the first child, second child, third child, fourth child, fifth child, sixth child, seventh child. And we can try to enumerate these possibilities, because remember, what we want to know is what is the probability in a family of 7 that 3 are girls. Okay. Well, what's one way? Well, one way, of course, is this way. Girl, 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 followed by boy, 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 boy. Okay, well, that's one way. And then you can imagine, well, suppose the first one's a girl, suppose the second one's a girl. Well, the third one, in fact, is a boy. Okay. And the fourth one is a girl. Okay, well, you can kind of imagine that just if you swap this one out, you can just put girls in each one of these places and count up all those ways. But then you could put a boy here, and then you could have 2 girls here, and then you could kind of girl, girl, move those ones. And you could quickly enumerate, well, I wouldn't say quickly, but you can enumerate all the different ways there can be exactly 3 girls. Okay, and then, of course, it would be the sum of all of those mutually exclusive probabilities, each of which, in fact, is, as we already said before, 1/2 to the 7th power. Now, I have a special trick for you, and I have a way of actually telling you how to count up all those numbers of children, okay, on all those different possibilities. Okay. What we're going to assume is, as I said before, with regard to Bernoulli trials, okay, the probability of excess is going to be equal to P, okay. The probability of let's call it a failure, is equal to, you could call it Q, or Q, or even more simply, 1 minus P. Okay, this is probability of success. This is probably a failure. And what we're going to consider is that there are a certain number of trials. These are Bernoulli trials, and we're going to say that there are n numbers of trials. Okay. Now, in this particular scenario, then, what we're going to do is we're going to say, what's the probability of 3 girls in a family of 7 children? And this is going to be equal to, okay, the number of trials, okay, and this is going to be 7 in this particular case, but we're going to call n equal to 7, okay? And we're going to use a formula. We're going to say it's n factorial, you know what a factorial is, divided by n minus the number of successes. In this particular case, what we're going to call is x. So x equals the number of successes. In this scenario, of course, is equal to 3 because we're saying having a girl is a success. So it's going to be n minus x factorial times x factorial. Now this looks kind of insane, but this in fact is all the ways, you'll see this in a moment, all the ways in which you can have this number of ways in which you can have 3 girls, okay? Times p to the number of successes, which is x, times 1 minus p, which is also known as q, to n minus x, okay? So let's just simplify this. So I'm saying there are 7 trials, so it's going to be 7 factorial, okay? Now, n minus x is the numbers of, so 7 minus 3, which is equal to 4, of course, factorial, times x factorial, which is the number of successes, 3 factorial, okay? Times p to the x, and so in this particular case, p is a half, okay? The chance of a girl is equal to a half, to the 3rd power, okay? Times 1 minus p, which is also equal to a half, okay, to the 4th power. And if you can think about it for a second, that's sort of the chance of boys. So what this is this is always what we said before. This is equal to 1/2 to the 7th power. But this big factorial here, which you can solve, of course, you can do it yourself, but this is all the ways in which you can get a particular number of 3 girls in a family of 7 children.